Welcome everyone to week 10 of the superstructure component of the structures 2 course. And in this week, we will be looking at week 10 content. So in week 10 content, we have some objectives like the possible failure mode for members subjected to bending stresses and check the beam for deflection serviceability and using the universal beam and column capacity table. So in this week, we will be looking at how to design the rafters or the beams of the domestic shed. So in this week, after this week lecture, you will be able to work on the design of rafter or beam B2 of the superstructure project. This week, I want you to watch the lecture and tutorial videos and read the lecture notes, and also read and download Appendix C of the Structure Design Action of 1170.0. I hope you have all download the standard, and also need to download the Universal Beam and Column Variability Table because we will need to use it during our beam design, and also read and download the Universal Beam and Column Capacity Tables. Also, there is some lateral torsion buckling videos to show you what is the problem we face when we apply load to the steel beams. And also you can watch this video about testing the steel beam to have a look about how the steel beams behave during the load application. Okay, so now we'll start going through the slides of week 10. I hope you can see the slides now. So this week we will be working through the design of beam or rafter. And I will explain the design of beam and rafter like by going through this solved example. So the rafter and beam similar to the beams you have in your project for superstructure, sorry. So today we will be designing a beam like this beam here, B1, and in your project you will be designing a beam like B2. Okay, so B1 and B2 are rafters or beams. So this is what we will be learning today during our lecture. So let's go through our example today. So in this example, we will again design a beam under the loads we have. So the loads we have in our course is dead load and live load and wind load. So we have three types of loads. So we need to design the beam due to the loads applied to it, dead load, live load, and wind load. The question or the example asks to design an intermediate beam, B3. So this is our B3. So we have beams in the shorter direction in the 16 meter, which is in this direction, like this one here. So all of them are B3. So we will design one of them because the one on the edge here and here is called edge beam or external beam. And the other ones on the middle here are named or called internal or intermediate beam. So, as you remember from our first few lectures or first few classes, B3 is carrying, or the internal beams carrying more loads because they are in the middle. So they are carrying half of the bay from the top, half of the bay from the bottom. That's why it's carrying this hatchet or this blue area. However, the beams on the edge are carrying only half of the bay from one side, so it's carrying less area. That's why the question asks to design an internal or intermediate beam B3 because it is more critical because it's carrying 7 meter from the roof. However, the edge beam carrying only 7 meter by 2 or 3.5 meter. Okay, so this is the location of the beam, and this is the load width or how much the beam carrying from the roof. And another assumption here, we need to assume that the beam to column connection for this beam are pin joints. So we assume that the connection here between the rafter or the beam, this is our beam, and this is our column. The connection between the beam and column is pin joint. Okay, so this is our assumption for this course because it will be more complicated to design the beam if it is not pin joint. Okay, so now if we look to this frame or this example, we have the beam span totally is 16 meter. So the total span of the rafter or the beam is 16 meter. The height of the column is 6 meter. The spacing between the beams are 7 meter. Another assumption given or another information given to us for the wind. The example asks us to assume the wind class as N1. In your in your project or in your calculation in the project, you have already determined the wind load and no problem with the wind class. So this is just an example to save time during the calculation. Now let's go through the solution. The first step in our solution is load calculation or calculation of loads. So this is the first step. Step one is the load calculation. So what again our loads we are considering for this building or this structure? Again, we have dead load and we have live load and we have wind load. So this is the first step. We need to find dead load and live load and wind load for this beam, which you have already calculated in part one of the project. So let's have a revise or revision about what you have done before. The first load is the dead load or the permanent load G, which include what? Just remember that this is a roof beam because we have two type of beam. We have roof beam and floor beam. The load on a floor beam different from the load on roof beam. So floor beam and roof beam, dead load and live load and wind load. For floor beam, we have only dead load and live load, so no wind. So for example, in your project, this is your project. So the beam here is a floor beam. This is what you are designing. The beam here is a roof beam. So when you are designing B2, B2 is a floor beam, so no wind load on it. So just to be careful when you are working on part 2 that no dead load on the floor beam. Another parameter or another information for you or another hint for you is The dead load and dead load here are different. So dead load and live load are different on floor and roof beam. So you can't use same dead load and live load for roof and floor because as we will see now, what is the component of dead load on a roof? For the roof, we need ceiling, we need insulation, we need surfaces, we need the weight of the purlins, we need the roof sheeting and self weight of beam. So all of this are the dead load G for a roof beam. For a floor beam, the dead load will include flooring. So you need to find a suitable material for flooring. Like for example, concrete or any other material. And you need beams or secondary beams or joists. So you can have secondary beams. And finally, the beam self weight or the beam or the rafter self weight. So just be careful between the difference of roof beam and a floor beam. Okay, so now let's continue. So the component of the dead load of the roof beam is including ceiling, insulation, surfaces, weight of purlins, and roof sheeting and self weight of the beam. So G total will be equal to G ceiling plus G insulation plus G surfaces plus G Berlin plus G roof sheeting and finally G beam or G rafter. So this is the total dead load. The second load we have for a roof beam is live load or imposed load Q. Q will be found using AS 1170.1. So this is how the live load will be calculating based on the use of the bill of this roof or the floor. So the live load is based on the use of the roof or the floor. The third load we have is the wind load, suction and pressure on the roof, W ultimate. WU is calculated using which standard AS 11 4055. So we have used this in part 1 to calculate the wind load on the rafters. So this is the component of dead load and live load and wind load. So now let's start with the first load we have is the dead load or the permanent load G. So G again, including ceiling load, insulation load, weight allowance for fixed surfaces, weight of purlins, and roof sheeting. And finally, plus we have another one which is self weight of the of the rafter itself. So as you can see in the diagram, in the pictures here, this is our roof sheeting. This is our ceiling, how the ceiling looks like. This is our insulation for the roof. Any roof should have insulation and ceiling. So you can't construct a roof without insulation because of the heat. So in the summer or in the winter, if it is the temperature is too low, so you need insulation to keep the warm and keep the temperature controlled inside the building. These are the surfaces which you can include like AC pipes or lines, and also pipes, electricity lines, and so on. This one is Berlin. So the roof sheeting is resting on what? The Berlin. So any roof sheeting will rest on Berlin. So you can't construct your roof without the Berlins. So let's start with calculation of the components of the dead load. So the first component is our ceiling. So where we will find the ceiling load from the Australian standard 1170.1 or from table A2. So this is table A2. I think you have used this before. So in table A2, you can assume a type of ceiling for your building. So I think you have done this already, but just a reminder about that or revision. So for ceiling, you can assume any of the available materials in the standard. So for this example, I have used the Portland cement plaster, thickness 13 millimeter. So we have used BCB, 13 millimeter thickness. How much is the weight of this material in the standard? 0.29. So from the standard, 0.29 kilonewton per square meter is the weight of the BCB ceiling material. So how can we find the ceiling dead load that will go to the rafter or to the beam? So G ceiling, we mean here that this is the ceiling weight that goes to our beam B3. So how we find that? If you remember, just quickly here, for beams, all the loads should be in what? Uniformly distributed load. So uniformly distributed loads. So the unit means in kilonewton divided by meter. So all loads should be in kilonewton by meter so that this is our final beam. For example, B3 or whatever the beam, we have a load distributed over its length or its span. So all the loads should be UDL and the unit is in kilonewton meter. Do you remember that? Any of you remember that? No? So our target when we are designing a beam to find all the loads in kilonewton per meter. Okay, so now how we convert this value 20.29 in kilonewton per square meter to kilonewton per meter using the formula here. I have write the formula for you here. So G ceiling will equal to the load from table in kilonewton per square meter multiplied by the load width of the beam in meter. So if you are multiplying kilonewton per square meter times meter, so how much is the final unit? Kilonewton divided by a meter. So this is what we want or what we need. So now if we go to the next slide, the weight of the ceiling will be G ceiling, the unit weight of the BC blaster, 13 millimeter, times the load width of the beam. How much is the load width of the beam? The load width of the beam will come from this diagram here. So this is our B3. B3 is carrying half span from this side, half span from the top side. So each beam carry half of the next span. So this beam have two sides, so it will carry half from top. How much is this half? This half is 3.5 meter. And another half from bottom. How much is this half? Another 3.5 meter. So how much is the total load width for this beam? 7 meter. So the load width of our beam is 7 meter. So now we will multiply the value from the table, which is 0.29 kilonewton divided by squared meter times 7 meter, give us the ceiling weight equal to 2.03 kilonewton per meter. This means that if this our beam B3, the span of B3 is 16 meter, the ceiling weight G ceiling on the rafter equal to 2.03 kilonewton meter. But this only the first component of the ceiling. So we will need to do this for all the other component as well. But just this is just example, or just the first component. So now the second component is what? Insulation. Insulation is also needed for the roof beam. So if you are designing roof beams, you need to assume insulation. Where we can find the insulation load? The insulation load can be found in table 1A1 in the Australian Standard 1170.1. So one of the hints you need to know, if not specified in your sheet or in your assignment, what you do, you can assume a slightly conservative insulation. So you can assume one of the insulations available in the market. For example, you can get it from table A1 of the Australian Standard 1170.1. So for this assessment or this example, I have used the insulation sheet here. The weight of this sheet is 6.9, but let's consider what is the unit for this one. So we have used insulation sheet. The weight per cubic meter for this sheet is kilonewton per cubic meter. So insulation or insulating sheet 6.9 kilonewton per cubic meter. So if the material is given to us in kilonewton per cubic meter, this means this not a load. This is density or unit weight. So we will need to multiply by a thickness. So for the insulation, the load of the insulation or G insulation will be equal to the value from table in kilonewton per cubic meter multiplied by the insulation thickness in meter multiplied by the load width. So the only problem or the only difference between the insulation and the ceiling is that we need to multiply by the insulation thickness. This is just because the table give us the value in kilonewton per cubic meter. So again, here is our value. So we will need to assume a thickness for this insulating sheet. So now, if we look to the weight of the insulation, we have the value from the table from A1 1170.1 multiplied by the thickness and multiplied by the load width. The beam load width doesn't change, so the load width is 7 meter. As you can see here, again, we have load width 7 meter like that. So this is the beam load width. Now, the only thing we need to do here is we need to assume a thickness. So what I have done is assume a thickness of 10 millimeters. So in this case, we have assumed the insulating sheet thickness is equal to 10 millimeter. 10 millimeter, we will need to convert it to Newton. How to meter, sorry. How to convert from 1 millimeter to millimeter? We need to divide by 1,000. So we need to convert the millimeter to meter, so divide by 1,000. So here what I have done, this is the 10 millimeter divided by 1,000 to make it in meter, multiplied by the load width in meter, 7. So the insulation load is 0.483 kilonewton per meter, which mean again, if this our beam, 16 meter span beam, the beam will be under G insulation equal to 0.483 kilonewton per meter. So again, our target for each load is to reach this step. So this is the load we got here. This was the load we got for what? For ceiling. So if all the loads have same unit, which is kilonewton per meter, so that we can add them together and finalize the load. So just be careful when you are calculating the loads that you need to find all the loads in kilonewton per meter. So now we got the load for insulation and for ceiling. What is the next one? The next one will be the surfaces or the fixed surfaces. In this slide, I have put a hint for you or like an explanation for you about the fixed surfaces to account for the surface's weight, such as lighting or water pipes and gas pipes and HVAC ducting and so on. We commonly assume a conservative value of uniformly distributed area load in kilonewton per square meter across the whole roof. This value can be taken as zero point 0.1 kilonewton per square meter. So we assume that we have a surface's weight distributed over the whole roof equal to point 1 kilonewton per square meter. This is like a common value or an accepted value to account for all the surfaces for this type of roofs. So this is the value we will be assuming for surfaces. So again, we need to convert this value to what? To the rafter. So this value now in kilonewton per square meter over the whole roof. So similar to before, we will need to find the surface's weight or G surfaces, which is the load of the surface that goes to our beam B3. So in this case, simple one, we have surface's weight in kilonewton per square meter. We will multiply by the beam load width in meter. So the beam load width, as we know, is 7 meter because this is the tributary area. If you remember the tributary area, so this hatched area is the tributary area of B3, and the 7 meter is the load width of this area. So if we multiply the surface's weight we assumed times the load width, we will find that G surfaces 7 kilonewton per meter. Or in other words, the load we will got from the surfaces on the rafter or the BMB3 will be equal to G surfaces equal to zero point 0.7 kilonewton per meter. So again, this is our final step to find the surface's weight. So for every component of the load, make sure that the unit is kilonewton per meter. So now we have found three components of the dead load. We have found the ceiling and the insulation and the fixed surfaces. Now if we go back to our component, so we have got the ceiling, we have got the insulation, we have got the surfaces. We still need to find the weight of purlins, roof sheeting, and the self weight of the rafter. So now we have the weight of the purlin. So the next component we need to find the load on from is the purlins. Before we proceed, just a reminder, what is the purlins? The purlins are, or the purlin is a horizontal member, so it is like a beam. So the purlin and beam are similar, but just the purlin is the member that carries the sheeting. The beam is the member which is carrying the purlins. So it is a type of beam, horizontal member, which carries the roof deck or the roof sheeting loads. And it is supported by steel beams or rafter and trusses. So the purlin is mainly or only used, this term is used for roof. So no purlins in floors. Okay, this is just the terms to select the correct terms in your calculation and in your design. And this is two diagrams show us what is the purlin and what is the beam. So if you look to this one here, so this is our rafter. So this is our beam or rafter, and this is our columns or our column. The purlin is the member resting on the rafter like that. So this is your purlins. So the purlins are resting on the rafters. Then after that, on top of the purlins, we will apply our roof sheeting. So this light green will be our roof sheeting. Okay, and this is, or those are our purlins. Another example here, this is our rafters, and on top of that we have the purlins. So these are our purlins. So the purlins all the time are perpendicular to the rafters. They cannot run in the same direction. So the purlins are perpendicular to the rafter. Then above the rafter, as you can see here, we have the roof sheeting on top of the purlins. So this red is our roof sheeting. This is just a reminder about the purlin. We have studied purlins before, so a reminder of what is the purlin. Okay, now how can we find the weight of the purlins that go to the rafter? So to find the weight of the purlins, we need to know what are the common section used for purlins in the market. So the purlins can be Z or C section or Z section. So this is the common members you can have. As you can see here, we have C or C. Here we have Z. Here is a hint or a advantage explanation of what is the advantage of Z section over C section. What do you think the advantage is? The advantage is that the Z Berlins can be labbed in continuous span so that we can increase the capacity. However, C Berlins cannot be overlapped. So the disadvantage or the advantage of the Z section over the C section that they can overlap, similar to this example here. So as you can see, this part we have double or overlapped two purlins. So this will help us to make continuous beam purlins and will increase the capacity of the purlin. Okay, here is the C purlins. As you can see, we need a connection between them. So C purlins need cleat sheet or cleat connection between them to connect. So no overlapping for the T purlin, but both of them can be used. But it's just an like explanation of why the Z purlin may be more preferable in the market or in the construction industry. So guys, do you have any question before we proceed? No question? Are you here? Do you hear me? Okay, thanks, Lewis. I just make sure that you are here because I haven't received anything from you until now. So all good up to now? Okay. Thank you, Silk, for confirming. Thanks, Lewis. Okay, so now we know what is the Berlins available in the market. And the next step is we will need to assume one Berlins to uh, to continue our calculation because in this course we are not designing the Berlins. That's why we don't worry too much about the size of it. But to continue or to proceed with the design, you need to assume a Berlin. So the Lysat Berlin is one of the, or Lysat is one of the providers or the manufacturer of the Berlins. You can find the brochure for their Berlins using this link. And these are the shape of the C and Z Berlins. And just some information. The Berlins are galvanized section or actually from cold formed steel. This steel is galvanized with a layer of galvanization. And usually we use the bolted connection for this type of uh, sections. The nominal length for the Berlins is 12 meter or 12,000 millimeters. So this is the standard length for the Berlins. If you need more size, you need to talk to the company if they can produce for you. If you need less size, so they can cut it for you. And here is the standard range of Lysat Z and C for 100 millimeter, or all these values are the height. So this is the height H. So if the height 100 millimeter, you can have 1 millimeter thickness or 1.2 and so on. For 350, they can only make it from 3 millimeter. So this is the available range in the market. And now if we go to the table, so this is the dimensions and mass of the Z and C Berlins. So again, as we are not designing the Berlin. So what we should do, we will assume the cross section of the Berlin from our experience as we are not designing it. So for this example, what I have selected is this size. You can select any size for your calculation because we are not designing it. So what we have used is we used C or Z 224. The mass of this equal to 7.2 kilogram per meter. So the mass for this Berlin is 7.2 kilogram per 1 running meter. So now after we assume the Berlins and we know the mass per length, how can we find the weight of the Berlins? To proceed with the weight of the Berlins, one important step you need to do, this important step for the weight of the Berlin, which is the number of the Berlin. So you need the number of the Berlins to find the weight of the Berlins. So if you remember this calculation, we have done this earlier in the first 2 or 3 classes. So if you remember, we have this example here, or let's add a layer, another slide. So if you have a rafter, so this is a rafter, this is your Berlins. Let's assume number of Berlins. So those are the Berlins. So if this is the span of the rafter, so we have two types of Berlin spacing. We have internal Berlin spacing, just black ones, internal spacing, which we will assume it as X. And on the edges we need to assume different size or different spacing, which is a little bit less. We call this external spacing, and this one is external spacing. How much is the external spacing if you remember? 0.75 from X. So it is a little bit less to account for high wind on the edge. So now for this example, if you look to this example, our span should be equalized to 2 external spacing and 2 internal spacing. So 2 internal spacing plus 2 external spacing, right? So this is internal and this is external. So your span should be equal to 2 plus 2 times 0.75, so 2 plus 1.5 x. So it becomes 3.5 x. So if you have a span, x will be the span over 3.5. This x should be in the range of 1 meter to 2 meter. So the internal spacing of the Berlin should be in the range of 1 to 2 meter. After you find x, then the external spacing will be 0.75 x. So this is how we work out the Berlin spacing. So now, if we look to our frame is 16 meter, but it is symmetric here, so we can work only on half. So how much is half? 8 meter. So if you look to the half, we assume that we have 5 or 6 Berlin, sorry, 2 on the edges and 4 in the middle. So that in this case we have 1, 2, 3 internal spacing, and what we have on the edges 2 in external spacing. So we have 0.75 x and 0.75x. So this is what we have done here. So we have assumed three internal spacing and two external spacing. So this is how you can assume. So now half span of the frame or 8 meter will be subdivided into some internal spacing and some external spacing. For internal spacing, we have assumed 3 here, and for external, we have assumed 2. One general condition, x should be in the range of 1 to 2 meter. So we assume that we have 3 internal spacing and 2 external spacing. So we have 3x for the internal spacing and 2 times 0.75x for external spacing, totaling 4.5x. So now 8 meter should be equal to 4.5x. This will give us x equal to 1.78 meter. So 1.78 meter is correct or acceptable or not? Is this good or not good? It fell in the range of 1 to 2 meter. So this is good number or good value of the spacing. So now the external spacing is 0.75x, which is 0.75 times 1.78. So the external spacing is 1.33 meter. So the internal spacing 1.78, external spacing is 1.33. So this one is important part of the calculation. So internal spacing 1.78 meter, external spacing is 1.33 meter. So these are our values for the Berlin spacing. And how much is the number of Berlins we have assumed for this building? 1, 2, 3, 4, 5, 6. So 8 meter of the frame or the rafter, sorry, or the beam includes 6 Berlin because the number of Berlins is important for our calculation. So we have found the number of Berlins now. And then the next or the final part of this calculation is how much is Berlin's weight. So the Berlin weight will be using this formula here. G Berlin equal to the weight of Berlin in kilonewton per meter times the load width in meter multiplied by number of Berlins divided by beam length. So the idea is in this direction here, if this our half, so how many Berlins in this half? One, two, three, four, five, six. So we will multiply weight of the Berlin times the load width because this is our load width multiplied by the number of Berlins divided by the beam length. Because if you look to our beam tributary area, okay, the idea is we are like counting how many Berlins inside this load area. How much in half? We have 6 Berlins in half. So that we need to divide the number of Berlins divided by the beam length. Okay? Just saved a question. How did we get the number of Berlins? Just assumed. How I assumed this one here? We assumed that we have 6. One option to assume the number of Berlin is divide the width. This how to assume. assume Berlin's number. You will divide the beam width, which is here half is 8 meter, divided by the range. What is the range we are looking at? 1 to 2. So we can take an average of 1.5 meter. So 1.5 meter is the average Berlin spacing. So if you divide 8 by 6, oh sorry, 8 by 1.5, this will give us 5.333, which we can round up to 6 Berlins. So this is how you can assume it. But for your project, if you want, because all the beam widths are close, so you can assume 5 maximum or 4 to 5 Berlin. But this is the best way to roughly assume the Berlin number. To divide the beam width over 1.5 and round this up. I think we have mentioned this in one of the classes before, but maybe you forget it. Okay, is it clear now? Yes. Okay, thank you. So the idea is we can assume any number of Berlins, but our restriction or our problem is we need to keep our Berlin spacing in this range. So we can't have a Berlin spacing of 4 meter or 3 meter or 5 meters. So we can maximum 2 meter. So that this equation on the top here is a good way to make assumption. Okay, so now if we go back, you know now how much is the Berlin number? Number of Berlin is 6. So from the table, because we have a small trick here, the table give us mass of the Berlin. So the mass is 7.24 kilogram per meter. So we need to convert it to kilonewton. How to convert this to kilonewton? We need to multiply by 9.81 divided by 1000. So this one will convert the value to something in kilonewton per meter. So this is what I have done here. We need G Berlin, so 7.85 kilogram per meter multiplied by 9.81 over 1000 give us in kilonewton per meter times the load width, which is 7. So this is the weight times 7 times number of Berlins. How much is the number of Berlins? Or how many Berlins we have? Here we have 6 Berlins divided by the beam span. How much is the beam span? 8, half. Because half we have 6 Berlins. If you take 16, so you need to take 12 Berlins. So now G Berlin equal to 3.82 kilonewton per meter. Any question about the Berlins? So the final answer means if our beam is 16-meter beam, we will have G from Berlin's or dead load from Berlin equal to 0.372 kilonewton per meter. So this is our target. So all these steps just to reach to this value. Okay. Any question? Okay. Thank you. So if we return back to our dead load list. So now after we got the Berlin weight, so we still have the roof sheeting and the self weight of the beam. So the next one will be the roof sheeting weight. So the roof sheeting weight based on the roof sheeting profile. So in your case, for beam B1, what was the roof sheeting you selected? It was given to you, right? But here in this example, if it is not given, so what we need to do, we need to select a suitable roof sheeting profile. If you remember, we were selecting based on what? The Berlin or the maximum spacing of support. What is the supports Berlins? So if you remember this class, we have looked at the internal spacing and the end spacing. Here, what is the maximum? This is the one I have selected, custom blue ORB. If you look here, here we have 1800 maximum spacing. Our internal spacing is 1780. So this one is okay. So 1800 is okay. The maximum end spacing is 1600. Our in the Berlin spacing was 1.33 or 1330. So this one is also okay. So to select, you need to compare the internal spacing you got, which is 1780 millimeter or 1.78 meter with 1800. If it is less, okay. Also compare the external spacing. How much was our external spacing? 1330. Compare with what? 1600. If it is less than 1600, so it is okay as well. So this is what I have done here. So now we have selected which profile we will be using. The mass of this profile is 6.1 kilogram per square meter. So to find the roof sheeting weight, I have assumed using custom blue ORB, mass of 6.1 kilogram per meter. The formula for roof sheeting weight, G sheeting, is the load from table in kilogram per square meter. We need to multiply by, sorry, we need to multiply by 9.81 and divide by 1000 to convert from kilogram per square meter to kilonewton per square meter. What to do? We need to multiply by 9.81 divide by 1000. Then multiply by the beam load width. So all the loads should be multiplied by the beam load width to convert from kilonewton per square meter to kilonewton meter. So again, because all the loads we have are distributed over this area. What is the width of this area? 7 meter. So from the table, the mass is 6.1 multiplied by this value to convert, multiplied by 7, which is the load width. So the final roof sheeting load is 0.42 kilonewton per meter. So again, this means that our rafter, 16-meter rafter, will have G from the sheeting or the roof sheeting equal to 0.42 kilonewton per meter. And this is our target from this step. Okay, so this is the load component for the roof sheeting. Any question about the roof sheeting? No? Okay. So now what is the last component of the dead load? Our last component of the dead load is the beam self weight. So the beam itself has self weight, so we need to includes the self weight in our calculation. So how can we find the beam self weight? Do you know? At the moment, at this stage, we haven't designed the beam yet. But to proceed, we need to make a selection or an assumption. So you need to assume a beam. So what I have done here, go to the rafters or the tables for universal beam. This table can be found on the course website. So for rafters or for beams, what we are using? We are using universal beam section. The universal beam section abbreviated to UB. So what I have done, go to the universal beam table and select one of the beam. One of the beam is 360 UB 56.7. For your information, this part is the mass of the member. This part is the height. So this is how they name or give name to this member. So just for this example, I have used this member here. So what is the mass for this member? This is the mass. So G rafter will be, the problem here is the mass is given in what? Kilogram per meter. So we can't work on kilogram per meter, so we need to convert to kilonewton per meter. How we convert to kilonewton per meter? We multiply by 9.81 divided by 1000, similar to before. So what I have done, just get the value from table, multiplied by this value to get the final load. So the final load we have on this rafter of 16-meter length is G self weight of beam equal to 0.556 kilonewton per meter. So this is our load. Okay, so this means that we have found the beam self weight. So if I ask you, if we go back from our first step up to now, we have got or we have calculated all our load. So weight of ceiling, weight of insulation, weight of surfaces, weight of purlins, weight of roof sheeting, and self weight of beam. So if I ask you how much is the total dead load on the rafter B? The total dead load on the rafter B3 or on beam B3, G total will be the summation or adding all the dead load we have calculated. So we have ceiling load, insulation load, surfaces load, purlins load, sheeting loads, and rafter loads. So the ceiling load was first step 2.03, insulation was 0.483, surfaces 0.7, purlins 0.372, cheating 0.42, and finally rafter is 0.556. The main thing I want you to notice is all of them should be same unit to be able to add them together. So all of the loads are in kilonewton per meter or uniformly distributed loads. So this is the main thing you need to be careful when you are doing this calculation. So the final answer or the final load is G total equal to 4.56 kilonewton per meter. So our beam, 16-meter length, will carry dead load equal to G total equal to 4.56 kilonewton per meter. So this is our final dead load. So all our step was just to find the total dead load, G equal to 4.56. And usually the dead load is the most like or the load that will take more effort to calculate. For live load and wind load or for live load will be a little bit less calculation. So the second part of our calculation will be our live load or the imposed load. The live load takes the symbol Q, where we can find the live load from the Australian Standard AS 1170.1 table 3.2. So table 3.2 for what roofs? So again, be careful when you are calculating the loads for your assignment. B1 or here B3 is a roof beam. So if the slab or the beam supporting a roof, so the live load will be using the formula from table 3.2. The formula is 1.8 divided by A plus 0.12 in kPa and should be more than or equal to 0.25 kPa. So this formula for what? For a roof beam. For a floor beam, it is different calculation. So just be careful when you are doing this calculation. So now for our live load on a roof beam, the formula is like that from the standard and not less than 0.25 kPa. So what is the target we need to find? The target is we need to find live load on B3. So the live load should be in kilonewton per meter, not in kPa. So just be careful when you are doing this calculation. So the first thing is we will find Q in kPa first and then convert to kilonewton per meter. So 1.8 divided by A plus 0.12. What is A? A is the plane projection of the surfaces area of the roof supported by the member under analysis in square meter. So actually A means the tributary area of B3. So this is what is meant by A in this formula. So this is our tributary area. So the dimension of this area is 16-meter width and 16-meter length and 7-meter width. So A in this case is 16 meter times 7 meter. So Q will be 1.8 times 16 times 7. This is A plus 0.15. So the value is 0.15 kPa. We can't use this value because 15 less than 0.25. So this means our final value is Q equal to 0.25 kPa. And just a reminder that kPa is equivalent to what? Kilonewton per squared meter. So we have got Q equal to 0.15 kilonewton per square meter, but this not accepted. So we take it as Q 0.25 kilonewton per square meter. Again, this value, not the value we need. We need to convert this value to kilonewton per meter. How can we do that? So Q on B3 will be equal to Q in kilonewton per square meter multiplied by the beam load width. So anything in kilonewton per square meter, we multiply by the beam load width to convert it to kilonewton per meter. So now if we return to our slide, we will multiply 0.25 kilonewton per square meter times the load width in meter. So how much is our load width? 7. So the load width of the beam will stay the same for all your calculation. So our Q on B3 is 1.75 kilonewton per meter. So if you use the value of 0.25 kVA, this means that it is not correct because we should give it in kilonewton per meter. Okay. Any question about the dead load, the live load, sorry? Okay, so the next one will be the wind load. The wind load, we have already done this before, and actually you will don't need this in design of B2, no wind load, because B2 is an internal beam and it is a floor beam. So it is inside the building. So if the beam inside the building, so no wind. So no wind load for B2. So you don't need to calculate any wind load or include it in the design of B2 in your project, the superstructure project. Okay, now let's continue our problem now. So for our beam B3 here in this example, B3 is a roof beam, so we have wind load, but we don't need the calculation in detail, so it is given to us that the wind class ready is N1. So if the wind class N1 from the standard AS 4055, so what you need to do is go to the table 2.1 to find the ultimate and serviceability wind speed. So you will have two values for V. We have VH ultimate 34 and VH serviceability 226. The first one will be used in our strength or moment design for rafter. The second one, this value, this value will be used for serviceability or deflection design. Okay, so we have serviceability or deflection check. Okay, so I think you have done this already for B1 in your project. So after you get the speeds, so you have to find what the pressure. Q U equal to 0.5 times rho air multiplied by VH squared divided by 1000. So this is what we have used here. We will use two values for VH. One of them as 34 meter per second, one of them as 26 meter per second. That's why for ultimate limit state, we will have this value here. So the pressure is 0.69 kPa. And for surfaceability limit state, we will substitute with 26 meter per second. So the value will be 0.41 kPa. So that's why the standard give us two speeds to calculate two times. So for wind load, we have two wind pressures. Then the next step after you got QU, if you remember, the pressure equal to, or the wind pressure equal to QU times CB, where CB is what? CB is the wind pressure coefficient. So B is the wind pressures we need equal to Q. We have got two values for Q. 0.69 kPa and 0.41 kPa. So I think you have already get the CB values or coefficient before in part 1. So from table 3.1a for the pressure coefficient for wind, you will need to find the net pressure coefficient. Now we are only designing for what? For roof. We are not, it's not required to find the wall. So the roof factors are negative zero point 0.1 and, sorry, negative 1 and positive 0.63. So we have negative 1, positive 0.63. If you remember, negative means suction or outside of of the surface. Positive means pressure or into the surface. Okay. So then after we have found all of that coefficient, so the net pressure, we have found the net pressure. So again, just a reminder, we are working only on the net factors for general areas. So net pressures and for general areas. That's why we got these two values. So general areas and net pressure will give us these two values. Okay, so now we have got the coefficient and the value of QU. So the design wind pressure B, normal to the surface, according to the formula, will be 0.69 times 0.63. This give us 0.43. So this 2 is for what? From the ultimate value. So this is here, ultimate wind speed. So this 2 from ultimate wind speed. So what we have done is just multiply the value times the two coefficient. So this give us two values for pressures or wind pressures. One of them is positive. Positive means pressure. Negative means suction. The pressure is downward and suction is upward. So this is the two values for ultimate wind speed. We will need to do the same for the surfaceability, but later. So this is the pressure. How to find the wind load? Any wind load in kilonewton per meter equal to what? The wind pressure in kPa or in kilonewton per squared meter times the load width of the beam or the column in meter. So how much is our pressure? Our pressure is 0.43 for the suction, for the pressure, sorry, the first case here. So this is a pressure or downward. And another one is suction. So this one is suction or upward. So for any rafter, you will need to find two values of wind load on the rafter due to ultimate. So this two is for ultimate. One of them is upward, one of them is downward. So this one is downward according to this one or using this one. Another one is upward, sorry, using this value here. Okay, so this is our wind loads. So if we add one slide here on the rafter, wind load on B3. On the rafter, you will have two cases. One of them is downward. So the load, if this your 16 meter, so we have downward load. How much is this downward load? It is the first one here, 3.01. So 3.01 kilonewton per meter. The second case is upward. So we have same beam. This is the only weight or the only load you will have is acting upward. This one is WU upward, which is equal to, as you can see here, 4.83. So 4.83 kilonewton per meter. So this is the upward case in yellow. And we have another case here in pink to relate with the previous slide. Okay, so now we have got all the loads and we just have a comment here or a hint here, assumption in this example given to us. The beam to column connection are bend joints. So we can assume our beams or rafters as what? Simple beam. So this hint here was very important to us because it will affect how the beam will look like. So our beam will be like that. So this is our rafter. And because here bend and here bend, so we can assume it like that. How much is the span of this beam? 16 meter. So this is the shape of the rafter. But for simplicity, for design procedure, we will consider them horizontal beam. So that our beam will be assumed to be a normal beam, similar to what we have in the previous classes, in the last two classes. A beam very straight or no broken beam, just for simplicity. So for simplicity, we have convert our beam to a simply supported beam. So now to summarize what we have got up to now here, we have got G, dead load, Q, and wind. So G, this is our rafter. This is our rafter. And how many loads we have for wind? 2. So for G, how much is the load? It was 4.56. downward. So all the dead load and live load all the time are acting downward. So 4.56 kilonewton per meter. This is our G. For Q, it was a little bit lower, but still downward. 1.75 kilonewton per meter, which is Q. The third one is the wind load. We have two cases for wind load. One of them is wind downward, equal to 3.01 kilonewton per meter. Another one is upward, or W ultimate upward, equal to what? 4.83 kilonewton per meter. So these are the loads we have got up to here. So this is the loads. Now the next step is the standard have another theory about how to add the load together. So we are not adding the load just G plus Q plus W. So because some loads are not acting all at once. So not all the loads will act at once. So that the standard give us what something called load combination. So load combination is how to combine the loads you have G, Q, and W together. Okay, to see how much the effect or how what is the maximum effect. This can be found in 1170.0. So the standard that give us the root combination is 1170.0, section 4.2.2. So section 4.2.2 is the section that give us the root combination. So in this standard, you will find two types of load combination. This one is called strength load combination. So the strength load combination is what we are doing now. This strength load combination will be used to find what the moment and shear on the beam. So just to make sure that you understand this part, so we will be only using the strength load combination in this slide to find what the load, the moment, and shear. And later we will have another load combination where it is here, another load combination to find the deflection. So we have two type of load combination. One of them is the strength load combination, as you can see. Another one is the serviceability load combination. So the standard give us 5 load combination. Number one is 1.35 G. So 1.35 G means 1.35 times the dead load you have got. So this give us a value of 6.1. Another one is 1.2 G plus 1.5 Q. So 1.2 from G and 1.5 from Q give us another value 8.1. The third one is 1.2 G plus 1.5 epsilon L Q. Epsilon L is a factor for long-term load. This factor will be found also in AS 1170.1. So for example, here for roof, how much is epsilon L? Epsilon L is 0. So if epsilon L is 0, so this term will be 0. So the value will be 1.2 multiplied by 4.56 give us a value of 5.47 kilonewton per meter. Okay. The third one, or sorry, the fourth one is containing W. What is W? W is the wind load. But here we have a hint or something you need to know. W here in number 4 is W downward. Okay, so we have what is the value for W downward? This is the value for W downward. So we have 1.2 times G plus 3.01 WU downward multiplied plus 0. 0 is also another factor, psi C, factor for combined load, also from AS 1170.1. Here again, psi L is 0, so this term will be 0. So the value is 8.48. The last combination, number 5, is 0.9 G plus psi, plus WU. WU in this case is what? Is the upward wind. So we have two winds, one of them downward, one of them upward. Downward will be used in combination number 4, upward will be used in combination number 5. So here we have zero point 0.9 from G minus. Why here minus? Because it is acting upward. So we have 0 0.9 times 4.56 minus 4.83. So the value is negative 0.73. So negative means upward. So now from this 5, we will select two values or two direction of values. The first 4, all of them are downward. So we select the maximum of this. Which one is the maximum? We have 6.1, 8.1, 5.47, and 8.4. So the maximum is 8.48. And here we have only one value for what? For upward. So this value is the value for upward. So the first one here is maximum downward, and this one here is maximum up. But also you need to know that if we don't have wind, what do you think? If no wind, similar to B2 in the domestic shed you have. So how many loop combination we have? 3. 1.35 G, 1.2 G plus 1.5 Q, 1.2 G plus WU, sorry, not WU, plus 1.5 psi L Q. So number 5, because they have wind, they are not applicable. So how many load combination you have in your assignment or in your project? 3. So now if we return it to our project, our example here, so what we have selected is two values. The value of the pink is 8.48 and the yellow value is 0.74. So to summarize this, the load combinations we will be working on to design are two. The first one is downward, maximum downward. How much is the maximum downward? We have a load acting downward, ED equal to 8.48 kilonewton per meter. Another case or another load combination upward, which is the load acting upward. So 0.73 kilonewton per meter. Okay, so this is the load combination. So after you find all the loads, you need to find the load combination based on this five. Then after that, we will work on the rafter design. So to design the rafter, we have two cases. Case one, when the top of the beam is under compression, or we can summarize it in the downward case. So in the downward case, this is our load. So the load is acting downward, the one we have drawn earlier. So we have 8.48 kilonewton per meter. So in this case, we have a problem with the compression, because if you look to the videos on the course website, you will find that when we apply a moment to our rafter or our beam, this moment will cause tension on the bottom of the beam and compression on the top of the beam. So the problem is we have a problem with the compression of the steel. The problem is called lateral torsional buckling. So this problem only happened to what? The compression part or the compression flange, because the buckling happen only when we have compression force or compression stresses. So the idea is when we are designing, we are looking at or we are taking more attention to the compression flange. So the top flange in this case, or the compression flange in this case, is under compression. However, the purlins will provide lateral strains for rafting. So the idea is when you are designing I-beam under the positive or downward moment. So when we have the load downward, our compression flange will be the top, or our problem will be the top flange. Okay, so our problem is the top flange. So top flange will be under compression and will be subjected to lateral buckling. Because the moment will be acting like this. So the top flange will be under compression, the bottom flange will be under tension. How can this be improved, or how can this be reduced? The purlins, because we have the purlins are providing some support to the top rafter, or sorry, the top flange, because as you know, the purlins are running in this direction, right? So the purlin will provide support to the flange or the top flange. So the purlin will reduce, so purlins reduce the lateral torsional buckling. Okay, but we don't have purlin like continuously on the beam. The purlin are repeated every a distance. What is the distance? Here the distance is 1.78 meter. So we are worried about the distance between the purlins. So because this is the area where the beam is not supported. So here what is meant here is the top flange of the rafter is restrained against the buckling, And the maximum unrestrained length of the rafter is the Berlin spacing. Don't worry about that. We can work on the horizontal this. So I will update this one. So here is the thing we are the number I am looking at, or the number I am explaining to you. We have Berlins on the top of the beam, right? Those purlins will provide support to this point and this point. So we are worried now about only the distance between the points. This distance is the Berlin spacing. So the Berlin spacing, we have got it as 1.7 meter. This distance, or the Berlin spacing, is called the maximum unrestrained length of the beam. So how much is the unrestrained length of this beam? It is the distance of the purlins. Again, in this case, we can take it as 1.7 meter. It's actually more than this because of the slope, but we decide that we will work only on the horizontal distance, so don't worry about that. Okay, so now to design the rafter, the beam, we need to think to design the beam. We need the bending moment diagram, shear force diagram we have got last week in the classes, and also we need the unrestrained length of the rafter. So for the bending moment and shear force diagram, how can we got them? We will got them using the load combination we have got already. Then after we got bending moment and shear, we can design the beam using the unrestrained length. What is the unrestrained length for the downward case? It is 1.78 meter, or the Berlin spacing. Okay, so this was the first one. So we know already the Berlin spacing. So how can we find the bending moment and shear force diagram? So what you think? Do you remember this from last week class? So for simple beam under uniformly distributed load, if you have the load W, so the maximum bending moment under uniformly distributed load, this is a reminder from for last week. So we have W. So if the W go down, so the shear will be WL over 2 and WL over 2. The maximum moment in the middle will be WL squared over 8. So for beams, the shear diagram, we have two reactions. You can find the reaction yourself, up to you, or using this formula. So the shear at support will be WL divided by 2. W is the uniform load, L is the beam span. The bending moment at mid span is the maximum moment. How much is the maximum moment? WL squared over 8. So we have two important value, one for shear and one for what? For moment. Okay. The shear force diagram is two triangles. You have got this value here, connect with a line to the value here, and this is a positive value, this is a negative value. For the bending moment diagram, we have 0 here, 0 here, the maximum value WL squared by 8, and hang the parabola, or we have a parabola. Okay, so this is two important formulas we need to know about the bending moment and the shear. So now for our rafter, if I ask you, what is the maximum moment for this case? So for the downward case or downward load combination. For the downward load combination, this is our W. W here is 8.48 kilonewton per meter, and the span L is equal to 16 meter. So how much will be the shear and the moment? What do you think? The shear will be W L over 2, W L over 2. So shear force equal to W L over 2 equal to 8.48 times 16 divided by 2. So this value will be, is it correct or not? The shear is 67.84 kilonewton. Okay, so this for shear value. How about the shear force diagram? Leave this here. So if we want to draw the shear force diagram, see, so we will go up here from this point, up 67.84, and on the other side it will be 67.84 kilonewton. This is a positive and this is a negative shear. Okay, for the moment, if we put the moment above here, so bending moment, the maximum moment is WL squared over 8. So we have W 8.48 times L, which is 16 squared, divided by 8. So the bending moment value will be 8.48 times 16 squared divided by 8, which is 271.36 kilonewton meter. So this is the maximum moment. So if we want to put the bending moment diagram here, what is the maximum moment? The maximum moment will be in the middle here. The value is 271.36 kilonewton meter. And then we have 0 here, so we have a parabola. So this is the shear force diagram, and this is the bending moment diagram. Okay, so if we want to summarize this part here quickly, for the first load combination, downward, because in your project you have only downward load combination, so that's why I'm focusing on this one now. For the downward load combination, we have, this is our load, 8.48 kilonewton per meter. So the shear or the reactions are 67.84 kilonewton and 67.84 kilonewton. And we have the shear force diagram and the bending moment diagram. So the shear force diagram, the maximum shear is here at the support, 67.84 kilonewton, and the other side will be same value, and we connect with a straight line. This is a positive shear, this is a negative shear. For the moment, the maximum moment will be in the middle. The value is 271.32 kilonewton meter, and this is our moment. Okay, so this is the summary for what we have done for this beam up to now. So the next step, we will use this load moment to find the cross section, but I will leave this in the class tomorrow. We can continue the reminder in the class tomorrow. So do you have any question about that? So please, anyone will come to the class tomorrow if you can have a look on that so we can complete this in the class tomorrow. Okay? Because this example is important so that I want to make sure you understand it. Any question about this example up to now? We are finishing now, Yug. So we can finish now. Any question, guys, before we go? Okay, thank you, guys. See you tomorrow in the class.